Hello everyone. Today we are going to look at graphs and the first algorithm on graphs, breadth first search. When we study an algorithm, we want to know the purpose of learning this algorithm and which class of problems this algorithm can solve. So let's look at very first problem that we can solve using BFS. The problem is solving a maze. So the maze is given and you have an entry point in the maze and you want to exit from the exit point, and you need to solve the maze by rightfully choosing left or right at various decision points in the maze. For example, here you need to decide to go this way or that way. What we can do, we can model this problem as a graph where every choice point is a vertex and path connecting the points are edges. And your problem is to find the exit node and starting from the entry node. So this is the model of the problem. So we will use BFS to solve this problem. What BFS does? BFS traverses the connected component of a graph in the following order. First, you have an entry vertex, which you call it level 0 vertex, and then it traverses all its neighbor, which we'll call it level 1 vertices. Then once it's done exploring them, then it goes to level 2 vertices and level 3 vertices, so on and so forth. The above traversal defines a spanning tree of the graph. Now we need to think, how do you implement BFS? What we need to do is keep track of already visited vertices and visit vertices that are in the next level. So here is the algorithm, which takes 3 parameters as input. First is the graph itself, G, then entry vertex R, and the value X that you're looking for, that is level of the exit node. First, there are 2 local variables in your algorithm. One is Q, which is actually a queue, and a set visited, which maintains the list of nodes you have already seen. So initially, you insert the entry point in this visited set. Then you enqueue this R to your queue and you keep iterating until the queue is empty. Okay? So you just keep inserting vertices in this queue and keep removing things time to time and keep doing it until you exhaust this queue. So now queue is not empty, so you will enter in this loop at the first time. Then you dequeue an element, which is the top element on the queue, and check if this element is already has a label which you're looking for. If that is the case, then you're done. You just say, I found a vertex which gives you exit point, so you return that vertex. Otherwise, you look at all the adjacent node to V. Okay, you have that set, and then you pick an element from that set, W. Check if W is already in the set visited. If it's already in the visited set, you do not explore this node anymore, and then you skip. Otherwise, what you do, you add this node to the visited set. Now you say, I have seen this node, now I will never do this again. Okay, and then we add this node to your queue by calling enqueue function on the queue. So this is the algorithm that defines BFS. Let's try to understand what happens to vertex. What is the lifetime of a vertex? Okay, so vertex can be 3 possible states. First, it's not visited. You have not seen it. You don't know where it is. It is in that state. Now, some point of time, you go and discover it. That happens in a line number 10. So you have found this node, and you add that in a visited set and put it in the queue. First time it enters in a visited set, then it is also in the queue. This is because of line number 10 and 11. What happens is, some point of time, the node that you have inserted in the queue comes to the front of the queue. And once it comes to the front of the queue, it is dequeued. At that point, this is removed from the queue, but it remains in the visited set. When something is entered in the visited set, never leaves. So the third possible state, it has been visited and also not in the queue. Okay, well, let's look at an example. Okay, for BFS, a BFS being called with the graph G for our maze. Okay, and then we have entry point. Okay, so you send a node which represents the entry and the label of the exit. So what happens initially, Q, you insert the entry node in it. After dequeuing entry, you will add the neighbors of entry, which is only one node A, and you get inserted in the queue. Then what happens, you now insert the neighbors of A after dequeuing A, but entry has already been visited, so entry is not going to come back. So F and B are the only ones inserted. Now F is in the front, B could have been in the front. It's just arbitrary choice to insert F to be in front. The F is popped, all the neighbors of F are being added who have not been visited, but the set is empty, so nothing changes. Then you insert neighbors of B, which is D and E, and now E is in front, so E will be dequeued and its neighbors will be added, that's exit. But D is in the front, so D will be dequeued, its neighbors will be added, that's G. Next, you will dequeue exit, but then exit is the one you are looking for. Then the return of your BFS will be triggered, and you will return the exit node, and you'll say I have found the exit node. Now we have found the node, but we don't know how to get to the node because algorithm does not return the path to the exit node. It only returns the fact that you have found the exit node and the pointer to that node. But this may not be good enough. Somebody may want to say that, look, give me actual path that leads to the exit node. To do that, we need to modify our algorithm. We need to add this line. What does this line say? This line says that when you discover node W, who caused you to discover W? Somebody's neighbor was W, and that neighbor, when you visited the adjacent nodes of that neighbor, you discovered W, right? So that node is V, and so you need to keep that record. W.parent is V. W was discovered because of V, and that becomes the parent. And this actually, interestingly, gives you the path to the exit node. Let's look at in our example. So when we discovered A, it was discovered because of entry. F was discovered because of A. B was discovered because of A, and so on and so forth. Now you have a path from the entry to exit. Just walk backwards from the exit node to EBA entry, and you have the path. So now our algorithm not only can return the exit node, also the path from the exit node to entry. You just reverse it, you will get the path from entry to exit. Now we have understood the basics of BFS algorithm and how to not only search a node but also find a path to the found node. Now we are going to analyze this algorithm bit in detail and try to understand the various properties of this algorithm and prove a very important theorem which says that BFS always finds the shortest path.